Okay, welcome to this lecture on confidence intervals. And the first thing we need to do is we need to talk again quickly about the difference between Z and t-scores. So what's the intuition? So whenever the population standard deviation is known, you need to work with the z-scores. In case you do not know the population standard deviation, the quality of inferential statistics depends on your sample size. The greater your sample, the more representative it is. This difference in representativeness is captured by different distributions. Sampling distributions based on small sample sizes have a greater variation around the population mean than sampling distribution based on large samples. The t-distribution considers the difference in shapes of the sampling distribution. The greater your sample size, the more the sampling distribution approaches the standard normal distribution. And in fact, once your sample size is 50 or greater, there is practically no difference anymore between the t-distribution and the standard normal distribution. But nevertheless, if you don't know the population standard deviation, you should work with the t-distribution. So what I just said can be also visualized. So you see here that yellowish probability distribution, and that is from a t-distribution when the sample size is only 2. But you see here that this curve is labeled T, and then in parentheses, degrees of freedom, df equals 1. So when it comes to the mean, the degrees of freedom are always n, the sample size minus 1. Okay, then you actually can barely see maybe the orange curve, which is already pretty close to the standard normal, which is dotted, and the orange distribution line has 9 degrees of freedom, and that means the sample size was 10. And then you see a green line which has 49 degrees of freedom and which is based on a sample of 50. So it's the sampling distribution of something with a sample size of 50. And you can see that this distribution strongly overlaps with the standard normal distribution. So in other words, whenever you don't know the population standard deviation, you need to work with a t-distribution. But if your sample size is very large, there is really no difference anymore between using a t-distribution and a z-distribution. Because the greater is the sample size, the more the sampling distribution approaches the normal distribution. So now I just mentioned the degrees of freedom. And what that means is that the more degrees of freedom you have, that means the more variables can freely vary. And the more degrees of freedom you have, then of course the greater is your sample size. And when you have a greater sample size, that means that your standard error decreases. Because you know that the standard error from the sampling distribution is either the population standard deviation over the square root of n, or if we don't know the population standard deviation, we have to work with the sample standard deviation. So that means that if you have a higher sample size, we know that the standard error, which is the standard deviation of the sampling distribution, is either the population standard deviation sigma over the square root of n, or the sample standard deviation over the square root of n. So regardless of what we use, obviously if n goes up, then the standard error goes down. Okay. So, and the basic idea is the more representative a sample is, the less is the sampling error. The closer it is every time to the true population mean. Okay. So again, so standard error decreases as sample size increases, which is given by the formula of the standard error. And however, statisticians prefer to describe sampling distributions using degrees of freedom, not just sample size. And so what are degrees of freedom again? So if you know the mean of n observations, only n-1 values are free to vary. The nth value is then predetermined by the mean. So let's consider an example. Let's assume you know that the average age of 3 kindergarteners is 5. And let's say child 1 is 4 and child 2 is 5, but then it follows that child 3 must be 6. So that is then predetermined by the mean of 5. So therefore, for the sampling distribution of the mean, the degrees of freedom are n-1. And a general rule for the degrees of freedom is that we have the sample size, and then we subtract from the sample size the number of estimated statistics. So when it comes to a sampling distribution of the mean, we only estimate one parameter, which is the mean. So we have n-1 degrees of freedom. And there are other occasions, however, when we subtract more than 1 degrees of freedom. And that is the case whenever we need to estimate more than one estimator. And a classical example is, for example, a regression line. So a regression line would be basically derived from a scatter plot. So if you have a scatter plot where we have here x and here y, and then we have all those observations here, and then we try to fit the line of best fit, then we have here an intercept a, and there is a slope of b, and then we would say the predicted outcome of y is equal to an estimated intercept plus a slope times the value xi. So in this case, we estimate 2 statistics, namely the intercept and the slope, and the degrees of freedom in this example would be then n-2. So if we have a regression line that was derived from a scatter plot where we had, let's say, 20 dots, then the degrees of freedom would be 18. Okay, so here we have a look at the t-distribution and his father. And just as we can look up probabilities in a z-table, we can look up probabilities in a t-table, which however looks a little bit different. But before we take a look into the t-distribution table, let's quickly say a word about the inventor or the discoverer of the t-distribution. And that gentleman was William S. Gossett, and he developed the t-distribution when he was working for the Guinness Brewery. And Gossett actually wanted to publish his findings under his own name, but Guinness did not allow Gossett to publish his finding under his real name. And so he published it under a pseudo, and the pseudo was Student T, and that is why we have today the Student T. So what you can see is here you have a table which is giving you critical t-scores depending on the degrees of freedom that you can see in the first column. And then you want to know how much probability do you have in one tail. So very often we want to have, in the normal distribution, we want to have in one tail, for example, 5%. So then we will have in one tail 5%, but then in both tails together 10%. And then depending on the degrees of freedom, you can see the critical value that you can look up. In this particular t-table, from which I show you now an excerpt, you can see it also shows the z-table. And you can see if the degrees of freedom are very high, there's really no difference anymore to the value that Gosset's t-table would give you. And you can also see a picture of William S. Gosset, who lived from 1876 to 1937. Okay, I'll just show you the t-distribution. We probably won't work much with the t-distribution table because today we have things like Excel and we don't really need to have to rely on tables, but you still may see it in textbooks, which is why I wanted to show you. Okay, so when to use the Z and when to use the t-table, and I think it's already clear and I already have said it, so it might be repetitive. So you work with the scores whenever you know the population standard deviation, and this should say, of course, the z-scores. So whenever you know, so you work with the z-scores whenever you know the population standard deviation sigma. But of course, this is typically not the case. So otherwise, you need to work with the t-table or with a t-score. And once you have a sample size of 50 or greater, the difference between the z-score and the t-score, they really become negligible. And even some textbooks may say it doesn't matter anymore what you use, but to be on the safe side, if you don't know the population standard deviation, I would just work with a t-score. Let's do a little example of working with a t-score. And we want to know what's the probability of drawing from a population with mean 58, but an unknown population standard deviation sigma, a sample of n equals 9, with a mean of 61. Okay, so this is an awkward situation in the sense that we know the population standard deviation, but not, that's the awkward case where we know the population mean, but not the population standard deviation. So the sampling distribution now looks something like this. So I have to make it a little bit flat, but we have a normal distribution like this. And we know that the mean is 58. So we know that from the central limit theorem, the mean is an unbiased estimator. So the mean of the sampling distribution is now 58. But we don't know the population standard deviation. So we have to construct the standard error from our sample standard deviation, and that is 6. And then we have to divide by the square root of n, which is the square root of 9. So that means our standard error is 6 over the square root of 9, 6 over 3, so that's 2. Okay, so now we know that here you see the t-distribution, and you can see that the mean of 58 corresponds to a t-score of 0. And now we want to know what's the probability that we can draw from a population with a true mean of 58, a sample of 9 that averages out to 61. So here we have a mean of 61. Well, and that seems to correspond to a critical t-score of 1.5. So just like we construct a z-score, we always construct also a critical t-score, so maybe t-critical. So we ask the question, how far is our sample average away from a hypothetical mean? So now we need to say 61 minus 58, that gives us the distance from the mean, and then we divide by the standard error, which is 2, and then we get 3 over 2, which is 1.5. So that means we are interested in the area to the right of a t-score of 1.5 if we have 8 degrees of freedom. Because our sample was 9, so then we calculated the average from 9, that means we have 8 degrees of freedom. So the area to the right of a t-score, which is greater than 1.5, when we have 8 degrees of freedom, is between 5 and 10%. So in order to illustrate that, let's go back to the table. Okay. So we have a t-score of 1.5. So the first thing I do is I look up in the first column the degrees of freedom of 8. Okay, so that would be here. And then I look for the critical value of 1.5. So the 1.5 would be between the value 1.397 and 1.860, but it's difficult to read. But now we can see that 1.5 with 8 degrees of freedom, the t-table only tells us that in that tail to the right, we have between 10 and 5% probability mass. Of course, that's not very satisfying if we have only a range of 5% and we know it's somewhere in the middle. So that's why it's better to use Excel. And if we use in Excel the correct formula, which is t-dist minus 1.5, that's the critical value, because the area to the left of negative 1.5 is obviously the same as the area to the right of 1.5. So that's why I wrote here 1.5. And then Excel wants to know the degrees of freedom, so that is 8. And then Excel wants to know, is it cumulatively? Do we want the area? Or do we just the value on the y-axis? No, we want the area, so we enter a 1. And now we get the probability of 8.6%. So this area here is 8.6% roughly. And of course, that is indeed between 5 and 10%, as we have seen from the t-table. But of course, this is much more accurate than knowing it's between 5 and 10. Okay, so there is another question, which is how much different would it be if we knew that the true population standard deviation is actually 6? So if we know the population standard deviation, we have much less uncertainty. We don't have to estimate two things, like the sample standard deviation as a proxy for the population standard deviation and the mean. So now we would have to estimate only the mean. So in this case, we would write the standard error not as S, but as sigma. So then we would write it as sigma x bar, because we know it. But because sigma is presumably 6 as well, we will get the same critical value. But now we would have to look up the z-score critical, which is also the area to the 1.5. But it turns out that there is more certainty if we know the population standard deviation. So that means there is less spread around the mean, and the corresponding value associated with a known population standard deviation, the probability should be much less. And if we enter into Excel the function norm.sdist for the area to the left of negative 1.5, and again cumulatively, you see we get 6.7%. So then this area is actually much less. But of course we also have a different distribution, so the distribution would maybe look something like this. I'll try to draw it, but so there's maybe less uncertainty in the tail. So that's how you can think of it. So it shaves off some probability. Okay, so I hope that is clear how to distinguish between Z and T. And let's just stop here, and then let's continue with actually building some confidence intervals.